In this module, we're going to talk about path analysis and about mediation and moderation in particular, which are two very simple and powerful techniques for inference in the social sciences and now in neuroimaging as well. So there are two basic kinds of connectivity that we have been and will be talking about. The first kind is what we'll call the data reduction approach. And data reduction approaches identify distributed patterns in the data. They explain very complicated 3D, 4D, 5-dimensional data sets as a simple combination of, in our case, temporal components and spatial components and then subject level components. And these include standard and tried and true techniques like principal components analysis and independent components analysis. Partial least squares is a variant that takes into account multiple predictors on the data side and multiple outcomes. Multi-way algorithms extend beyond 2 dimensions. These include things like tensor ICA and parafac and factor analysis, and in-scale and out-scale, individual differences, multidimensional scaling. And finally, other techniques in the computational literature like self-organizing maps. And often graph theoretic approaches are applied to these maps in order to characterize the whole network properties, and that's increasingly popular now. The second family is the path modeling family. And the utility of this is to provide inferences about specific connections and associations in the brain and with physiology and behavior and experimental variables. And they include the following things. Path models are a series of linear models on observed variables, and structural equation models are very similar. They work on associations across variables. We'll look at a psychophysiological interaction analysis as a particular kind of path model. There's also spectral coherence models in the frequency domain instead of the time domain. And there's also Granger causality models, which can take into account cross-lagged correlations and autocorrelation, and dynamic causal models, which is part of a family of state space models that estimate relationships based on the dynamics or derivatives of the responses. These different approaches can be complementary. So, for example, you can use a data reduction strategy like ICA, come up with components, and then you can do path models or other kinds of models on those component scores. So this is really, I think of this as a toolbox for things that you can do to help understand your data and make interesting inferences. So we'll talk about mediation in particular here. And mediation is really an important concept, and we can think of it in part as a search for mechanism. So let's say I've got a manipulation of expected pain relief, and I'm observing some analgesia, pain relief. And we can think of mediating variables as those that might intervene and explain that effect. So this could be caused by less attention to the symptoms, altered valuation of pain-inducing events, and it could be caused by decision biases or other kinds of processes like that. When we apply this to brain analysis, a real advantage is that it can connect experimental design variables, brain measures, and outcomes in a single integrated model, where otherwise there would be a series of models. So here I've got an experimental manipulation, measures in a series of brain regions which are potential mediators of that effect, and an outcome, the behavior. So let's look in more detail at mediation. So mediation, the idea of what it's testing is, does this variable m explain some of the relationship between x and y? So this is really all about these. X is the initial variable, y is the outcome, these initial variable outcome relationships. And this can help establish a pathway that connects x to y through some intervening variable. So for example, in the brain, I might apply a stressor, that's an experimental variable, it's x. M is in its activity in the anterior cingulate cortex, and y is increases in heart rate. We also commonly refer to these paths, the relationships, by letters. So by convention, we'll say that the x to m relationship is path A, the m to y relationship controlling for x is path B, the original relationship from x to y is path C, and the relationship between x and y controlling for the mediator is C prime. Moderation analysis tests something that's different. What it's testing is, does the level of m, my moderator now, influence the relationship between x and y? So this can establish regulation of a pathway or conditionality of a pathway. And one common way to diagram it is like this. And in this case, for example, our stressor is a moderator. And now we've got the relationship between anterior cingulate activity and heart rate being different when stress is on versus off. and now stress is a moderator. So let's look now at test of mediation again. And one way to think about this is as a model comparison. So A, B, and C are all, and C prime, are all slopes in standard regression equations. So in the first equation, we take M, we regress M on X, and in the second equation, we regress Y, the outcome, on M and X together. So here's our linear modeling framework, Y equals X beta plus error. And in that kind of notation, this is what it looks like. I've got a vector of observations, M, the mediator. I've got an intercept and a predictor X, and those are each multiplied by beta naught, which is the intercept, times the intercept plus path A times X. The second equation looks like this. So now I've got an intercept, the X, and the M variables in my design matrix. And I'm estimating C prime and B, each controlling for the other. So a way to think about this model comparison is in terms of counterfactuals. So what we're doing is we're comparing the situation on the right, where there's just X and Y, giving us path C, with the situation on the left, where now I have some of that relationship going through M, through this mediating pathway. And so the counterfactual is, if we could put a clamp on M and prevent it from varying, would the effect of X and Y be reduced or absent? And if so, there's mediation. And if that's the case, then if we compare path C and path C prime, they should be different. And so we can test the significance of C minus C prime. And that's the test of mediation. And this, with some algebra, turns out to be the same as testing the product of the path coefficients, A and B. So we're really testing an A-B product in this case. So this is a directional model where I have to specify which is the predictor and which is the outcome. But one note of caution: it's better not to make strong directional interpretations about which is causing what, unless you're experimentally manipulating variables. And there has been a lot of debate and controversy about mediation, and as far as I can see, a lot of this controversy centers on whether you should make strong causal inferences when you have observed variables. And I don't believe you can. I don't think that means the models are not useful. I think that it just means that we have to be careful about the inferences that we make. So one thing to note here is that we can reverse the direction of the arrows and often get similar effects. We could reverse which is the M and which is the Y, and we might get similar effects as well. And one can test these different models, but it's important to know that the best direction, which model seems to give the most significant results, depends not only on the underlying strength of the relationships, but also on the relative error variances. So one variance could be greater than another one for uninteresting reasons. For example, if it's a brain region, it could just be a noisier estimate, and then it's going to look less like a mediator. And finally, causal inference is generally safer, at least, only if X and M are experimentally manipulated. So we can still use these as models of pathways, but perhaps without making strong causal claims. So a mediation test is a statistical test of A times B, and what that means is that we need to have an estimate A times B divided by some estimator of its standard error. And so this is the Sobel test, or the Arroyan version of it, several versions, and this says that the A times B divided by an estimate of standard error are distributed normally as a z-score. And then you can get p-values and make inferences. Well, A times B is not actually normally distributed most often. And so this test turns out to be over-conservative. And it's now typically replaced with a bootstrap test. And many people have worked on bootstrapping and mediation now. And there's packages available for that in multiple software packages. And now at the bottom, if we think about these path A and path B effects, it's useful to think about the families. This is a Venn diagram of the families of all the possible significant tests. So what you see here in the one circle marked A is all the family of all the tests that have a significant path A effect. And the green circle is all of the tests that have a significant path B effect. And a certain subset of them will overlap. You'll get A and B, the conjunction. And then a subset of those are going to be ones in which the A times B path coefficient is significant. So you can see from this that the mediation analysis is really a relatively conservative test for not only the presence of a path A and a path B effect, but also whether their covariances are strong, or whether the joint effects are strong enough to pass the mediation test. Let's look at a graphical example of this. So now we're working with our case where we have a stressor influencing anterior cingulate activity in the brain, which is predicting heart rate increases to the stressor. And this is what it looks like graphically. We'll first look at a case where there's mediation on the top panel. So now the blue dots are stress on, the green dots are stress off. And the path A effect is whether blue is higher than green on the x-axis, which is anterior cingulate. So we can see here, indeed, the blue dots are shifted to the right, so there is a path A effect. The path B effect is the effect of anterior cingulate activity on heart rate controlling for the stressor. So this ends up being a parallel slopes line or an ANCOVA model. And we can see the path B there is the slope of that line on average across the two groups. So that's positive. The more anterior cingulate, the greater the heart rate controlling for group. Path C is just the simple effect of stress on heart rate. So that's whether the blue dots are higher than the green on the y-axis, and indeed you see an effect here. And path C prime is the difference after you control for anterior cingulate, for the mediator. And so that's this gap between the two parallel lines. And as you can see here, the gap is very small. So we have a path C effect, and it's gone down to virtually zero, and that means that C minus C prime is greater than zero, and there's a mediation effect. So intuitively then, when we have a mediation effect, what are we doing? Well, what we're saying is that the effect of the stress on the heart rate is exactly what I'd predict based on the anterior cingulate activity. So I'm just shifting up along the anterior cingulate axis, and that gives me the significant mediation effect. Now on the bottom panel, let's look at a case where there are significant path A and path B effects, but there's no mediation. And in this case, it's a very similar situation, except that the effect of stress on the heart rate is so large, and the path A and the path B effects are relatively small, so they're really not sufficiently large to explain the effect. So what I'm left with is a big C and a pretty big C prime once I control for anterior cingulate activity. So that gap is still there, and that means that the mediator can't really explain a lot of that relationship.